Good morning, everyone. No. So no breakfast looks like. So how many of you did have breakfast? Also everyone. So again, good morning, everyone. Yeah. Okay. So what's the incentive of sitting in the back row? Like the view is good. Come front, come front. So there are places in the front. Okay. So today is the last day of the workshop. On present and future computing system. So I hope you enjoyed last 3 days, and today there is a exciting line of speakers. After that, we'll have an interaction session with our department's few of research scholars. They're either pursuing masters or PhD, and I mean they're doing some sort of research. So you'll have the opportunity to interact with them. I mean they will share their experience. You can also ask the questions. So you have to be there till that one, because that is the last session of the day. And then today is another important thing. Can anybody tell what is the other important thing today? Yes, you were saying something. Sorry? Yeah, last day, yes. But what's the important event today? Certificate. Yeah, yeah, please be loud. Why not? Okay, so few reminders, take notes, and again, you remember, right? What did I tell in the first day? That we will check the notes, and whoever has the notebook filled up, they only will get it. Is that fine with you now? Yes? Oh, who told yes? I think they have filled. You told yes? No? Okay, anyways. Yes, but again, I mean, why we are saying that take notes? Because when you go back to your institute, you will revisit those notes, or you will tell your friends, colleagues that see that that's what happened, right? Again, I mean, there were like 350 plus registrations. We had to cut down to 70, and I mean, it will be justice to those people who couldn't come only if you share your experience with them, right? Yes, ask questions. I mean, you should challenge the speakers that no, whatever you did is may not be correct. Tell me why you did it. So ask questions. I mean, yes, I mean on Friday you are asking questions. So today also I want to see the same spirit. Then, I mean, we have refreshment sessions like coffee break, lunch break, etc. So interact with speakers. I mean, there are lots of speakers today. Also, you are already interacting with each other, and past 2 days there was that CDAC hands-on session. You already interacted, but yeah, keep on interacting. Post your thoughts with hashtags. Our department is present at Twitter at the IISc. So, have anyone posted in social media about this workshop with hashtag? Okay, good. Where? LinkedIn. Okay. So yeah, as your name? Nandan. As Nandan is saying that he posted in LinkedIn, we are also present in LinkedIn at the rate Computer Science and Automation. So I would like to see more hashtags, more posts, more experiences, so that other people know about this workshop. Okay. We are also live streaming the talk the whole day on YouTube. So to see the live stream, someone has to subscribe to the CSA channel IISc. This is the agenda for today. So our first speaker is Meenakshi D'Souza. I would like to welcome Meenakshi, and when she is here, I would like to give a brief introduction of her. So Meenakshi is a professor at IIIT Bangalore and the secretary cum treasurer of ACM India. Her research interests are in formal methods, model-based development for embedded software, and software testing. She is also interested in gender diversity and accessibility issues in IT. Meenakshi teaches courses on software testing, automata theory and computability, discrete mathematics, graph theory, and design and analysis of algorithms in the institute. Meenakshi's course on software testing has been offered on the NPTEL SWAM platform. Um, Meenakshi also teaches in the online BSc degree program of IIT Madras. Prior to joining IIIT Bangalore, Meenakshi worked in the research department of Honeywell Technology Solutions, Bangalore, for 7 years on several applications of formal methods. So, welcome.
This way. Yeah, good morning to all of you. Thanks to Sumit for inviting me here. It's my pleasure to come to IISc. It's always a pleasure to come to IISc, and today happened to be extra nice because I didn't have to go to IIIT. It's a holiday there, so I could spend the whole day here. So it's nice. So today I'll talk to you about some work that we did along with a PhD scholar who graduated from IIIT year before last. Abhishek Singh, one of my past research scholars, works for Hindustan Aeronautics. It's a large public sector company based out of Bangalore. If you didn't know what they were doing, they do a lot of work with aircrafts and other things. So this is partly what I'm going to do is predominantly the thesis work that was done by Abhishek as a part-time research scholar in IIIT, where he essentially worked on formally verifying an operating system that was developed at HAL. So I'll start with a brief overview for those of you who are not very familiar with what is a safety critical software. It's just a one slider, and the kind of thing that we would be talking about is what we call an RTOS, a real-time operating system. And so I'll again have a one slider on one or two slides on what real-time operating system is, and to briefly tell you what is formal verification. If you had listened to Professor Raghavan on the first day, he would have spoken to you about program analysis, and that's one niche area within formal verification. Part of our work involves program analysis, but it's not formal methods is not just about that. It's more of that. And specifically, as a part of the verification effort, I would like to spend this half an hour that I have talking about two problems. We've looked at data races that would come in the kernel of the operating system that we had. And we've also looked at timing, verification of timing properties. So I'll delve into these two specific properties. Obviously, one cannot write a thesis by verifying one in-house corner or OTA. So you have to demonstrate that the techniques that you've developed also are useful for verifying a whole set of other real-time operating systems. So our work has been used to verify free RTOS, which is a very popular free operating system, real-time operating system that is there. Texas Instruments has its own RTOS. You can find its source code in the public. They've been kind enough to release it. So we verified TI RTOS. And Chibi OS is an OS that has hit popularity these days with a lot of unmanned aerial vehicles and a few other things. So our results have also been used to verify a few other real-time operating systems. Yeah. So what is an industry safety critical software system? Typical examples of these things are medical devices, devices that do surgeries, give radiation therapy treatment, and a few other things, where there's a lot of software. If the software fails, then it can have issues. In the past, there have been issues where people have died because of race conditions occurring in radiation therapy machines and stuff like that. Aircraft, several of the software that runs our planes are all safety critical in nature. They cannot afford to fail. Autopilot, ILS, instrument landing system, communication navigation system. They are all safety critical software, so correctness is at utmost important. Railway system, these days, autonomous driving cars, several different transport systems, military applications, nuclear power plants, all of these are safety critical systems. Basically, they are class of systems that are extensively controlled by software, and failure in these systems can mean loss of human life or loss of huge financial losses, but both of which cannot be afforded. So typically safety includes functional safety and quality, and off late there is a lot of talk on, there are buzzwords like safe AI. along with AI coming into the boom. And the scope of safety that we are talking about very much includes those AI-driven systems also. So these days, they not only use camera-based images, they use neural networks to make inferences on the camera images and then use that to make a conclusion about a control decision. So these AI systems or neural networks-based systems also have to be safe. And there's a whole plethora of research work that ensures that formal methods have work for these kinds of systems also. So we'll specifically move to one class of these systems. So many of these systems that I was giving as examples here, they are all so-called embedded systems in the sense that they are coupled to the platform on which they run. Contrast it to something like, HDFC Bank Online or Citibank Online, which is like a large web application that's also running as a part of an enterprise application. These are not that. These are embedded applications that are tightly coupled to their platform and they have their own features. And most of these kinds of embedded systems run on a hardware platform that is where there is a real-time operating system that runs, right? What are the features of real-time operating systems? They are basically have a lot of features that ensure the real-timeness of the application, the fact that it's deterministic and a few other things, niche kind of operating systems there. So there are several RTOSs that are famous, free RTOS, RTOS by Texas Instruments, VxWorks is a heavily commercial. RTOS Chibi OS is again on the partly on the free. And the RTOS that's of interest to us, that started as interest to us, is the one developed indigenously by HAL. HAL has invested about 8 years, I understand, from Abhishek on developing this RTOS. Now they have a single core version of this RTOS running on several systems. The multi-core version is under certification. So it's a completely indigenous in-house RTOS. And for those of you who believe in the Make in India initiative of the government, this is a classical example of what it could be. Right. So typically an application code for safety critical software runs on such an RTOS and is compiled along with the kernel library. There is a microkernel that runs on the RTOS. And there are multiple tools that directly can use the kernel API. So that's why I said it's slightly coupled to the platform on which it runs. Right? And these RTOS kernels are known to be notorious for their use of, they're like classical system software. So they use several low-level synchronization mechanisms. They can directly enable interrupt. They can directly disable interrupt. They can, preempt, switch on or off preemption. They can do a lot of things classically firsthand. And for several of these large, some of these are large RTOSs, some of them are small. There is a standard which interestingly was originated by a formal methods person called John Rushby long ago. And that standard is called IISc 653. It basically imposes very stringent requirements on how these RTOSs should behave in terms of the way they partition memory, the way they partition process space, and stuff like that. So the RTOS that's going to be the focus of this talk is the HAL RTOS. As I told you, it's the first indigenous RTOS developed in the country from scratch. And it's the first instance to be certified by CEMILAC. CEMILAC is a Center for Military Airworthiness. It's again, you just go down HAL airport, you'll get CEMILAC. It's a large center which is the counterpart of RTCA in the US. It does certification of these software. Now this RTOS is used by several organizations. This is a helicopter, IHawk series on which this RTOS runs, the HAL RTOS runs. You can see these helicopters in use, and you can also see them in the parade in Republic Day and stuff like that. It's used by BARC, it's used by military aircraft, military helicopters. Technically, it has a portable microkernel that's based on the IISc 653 specification. So we set out with this task of trying to see if this RTOS is functionally correct, and it was of course exhaustively tested. But there was a firm belief that testing cannot find errors, so we need to be able to formally verify it. So just to tell you briefly what formal methods are, think of them as a broad collection of techniques that need some amount of underlying mathematics, algorithmic, discrete kind of mathematics, very different from the maths that you see for machine learning and stuff like that. So the system that under verification or the software that is being verified is modeled. Some property of the system is also modeled using an appropriate mathematical language. And then the verification algorithm runs by checking some property of the system against the system itself. right? Please note that in general, this even though this looks like it's a very simple problem, we are dealing with a domain that has heavily undecidable problems. For those of you who know Turing halting problem, the problem of checking if a program halts on its input or not, just a very simple problem that you might think of, is itself undecidable. So we're talking about systems satisfying properties. So we are heavily on the domain of intractable or undecidable problems. The problems are either undecidable or they are intractable. Things cannot be automated that easily when you look at formal verification. That's something that you have to remember. So formal methods are largely manual, need a lot of human assistance, cannot be fully tool supported, and they're believed to be complementary to testing. Testing is a very powerful technique. Testing existed as old as software is, and I don't think we will ever reach a stage where we can develop software without testing it. And it is a single most powerful technique that's used to find loads of errors. But sometimes it can miss something because the strength of testing is in finding errors, not in showing correctness. So sometimes we might also want to show correctness. And when you want to show correctness and not find errors, you use formal methods. And this is just a piece of advertisement. The various works on formal methods. Turing Award is the highest award in computer science. And formal methods researchers have won 6 different Turing Awards. So it's an excellent area to work on if you're interested in higher education, right? So I'll just talk about a few techniques that we would be interested in. All these red colored things are techniques. What Professor Raghavan told you on the first day is another kind of technique that's also formal methods. So the technique that's the most expressive that you can do beautiful things with is theorem proving. Of course, it's the most expressive, so it's the least automated. And so theorem proving is basically what we call deductive verification. There are several beautiful proof assistants: HOL, Isabel, Coq, PBS, F star. F star is developed by a researcher, by a team that's based out of Bangalore from Microsoft Research. And it's a completely in-house proof assistant that's grown out of India. And Coq is a beautiful theorem prover for which several compilers have been verified. Each of them have their own beautiful stories to talk about. Some of them can be automatic, partly automatic. They need heavy manual assistance. What has caught the attention of the community in formal methods is these new class of things called SMT, satisfiability modulo solvers. There's a conference on SMT solvers that's coming up at IIT Bombay later this year, so you must consider going for that. It's a beautiful conference where you learn all the maths that is involved behind these SMT solvers. So it needs a lot of knowledge. You need to understand the underlying system, convert it, you have to write what to do and all that. Theorem proving specifically is never fully automatic, but it's a very powerful technique. For those of you who know a bit of graph theory, there was a four-color conjecture, which was ultimately proved to be a four-color theorem, and proof was done by a proof assistant. It was not a human proof. It was basically a proof assistant-assisted proof. And if you're interested in exploring more about theorem provers, there's a museum that you can refer to, and it really has the largest compilers of the collection of theorem provers that I've ever seen. Right. The next one is slightly more automatic, in fact, predominantly fully automatic, so least expressive in terms of what it can do. It's called model checking. It basically searches through the state space of a model. The state space could be explicitly modeled as a graph or could be symbolically modeled using certain binary functions, but it basically searches through the state space of the model and to see if the state space or the behaviors satisfy or violate certain property given in the temporal logic. It's often fully automatic. There are again state-of-the-art model checkers available. Spin is an old one, New Assembly, UPAL is for timed automata, Java Pathfinder, and so many of them are there, right? Firms like AWS, TI, Intel, they have dedicated teams working on in-house formal verification, including tools. Most of these places will have dedicated formal methods teams. And this is what Professor Raghavan talked to you about, abstract interpretation, a very specific technique. Apart from this, you have equivalence checking, runtime verification, then there are constraint solving. So many different techniques that exist in formal methods. Yeah, so now with that, let's move on to the problem that we have in mind. Remember, our goal was to verify several subtle properties of HALOS, and this was a certified RTOS, so it was thoroughly tested. and certified for all the parameters that it had to meet to be a highly safety critical system. But there was a belief that there were still subtle errors, mainly because it has this powerful microkernel which uses very low level synchronization mechanisms. So maybe some parts of the subtlety was missed in the testing. That's where formal methods can catch such errors. So I'll talk to you about two problems that we had worked on as a part of Abhishek's thesis. One is on detecting data races, and the other is related to timing requirements. So before we move on to how data races occur in the kernels of operating systems, we'll just understand what data race is at the highest level. So typically a high-level race will occur in an application if two pieces of code share a set of variables and communicate with each other by reading from the variable and writing back to the variable. So these are like global shared variables, and they communicate by reading and writing to them, right? And if you're not careful with the interleaving in communication, in the sense that certain parts of reading, writing should happen in a mutually exclusive way, in the sense that you should know that if a particular thread or a task is doing a write operation, then it should not be interleaved by another thread or another task. And if it doesn't happen this way, then it might end up causing atomicity violations. And the problem with RTOS kernels is that they have non-standard synchronization mechanisms. I'll tell you, I mean, in the sense that you can explicitly switch on the scheduler, switch off the scheduler. You can keep an interrupt open. They work in a very tightly coupled way. So they make race detection a little more challenging. So this is a generic example, toy example, not necessarily from RTOS. Let's say you have a situation like this. There is a common global variable called balance. Let's say whenever this program was running, balance had the value 100 in it. And there were two threads that had their own pieces of code. Yeah.
Could you please explain what atomicity violations are?
I'll tell you, this example will have that. There were two threads that were doing their job, and both of them were using this common global variable balance. So look at the code of the first thread. They try to be careful. The thread one takes this and it has its own temporary variable. So it copies the value of the temporary variable, then adds something to it, adds 200 to it, and copies it back to balance. Thread 2 also does something similar. It copies the value of balance to its own copy of temporary variable, local copy, subtracts maybe 50 to it, and copies it back to the balance. Balance is a global variable accessed by both the threads. So there is nothing here in the code that says who will run first, which statement of which thread will run first. It's just as it is, right? So if we start with a balance of 100, then let's say this is the kind of execution that happens. Balance is 100. First thread 1 runs, it makes its copy to temp 1 and adds 200. I think, yeah, it was adding 200 to this. And now temp 1 becomes 300. And then before it could finish this one, because there's nothing specified, let's say thread 2 starts running. Right? So thread 2 also makes its own copy, does that minus 50 and copies it back. Thread 2 finishes its all three statements, and after that thread 1 goes and starts running, right? And then thread 1 only has this last statement to finish, and thread 1 says, okay, this is it. But ideally, what the developer intended was that these 3 lines or whatever, some code fragment of thread 1 and some code fragment of thread 2 should not interleave. The statements from here should not get mixed up from statements from there. If something starts, then that thing fully runs, in the sense that it runs in an atomic way with no interleaving in between. And if another part starts, it fully runs. But for some reason, the developer had that in mind, just forgot to write it, let's assume for now, right? So this kind of thing happens, and this was completely unintended. At the end of this, the 100 was added to, or 200 was added, 50 was subtracted for something that was originally 100. And the resulting value became 300. This is not what was intended. The resulting value should have been 250. So what should the developer have, what should have happened? All the 3 statements of thread 1 should have run first, followed by all the 3 statements of thread 2. This is without atomicity. violation, right? But this wasn't specified in this code. So there was nothing that was specified. So any arbitrary interleaving can happen. Any kind of mistake can happen. This is just to illustrate that mistakes can happen. So ideally, what the developer should have done is, okay, this is my piece of code. There is some part here. Let's call that A. There's some part here. Let's call that B. And A and B statements from within A and B should not interleave. The developer should have done something to ensure that that happens. Right? That's what the developer should have done. So A and B are critical accesses because they both update a common global variable called balance. And if they both read from and write to, the other one, when one is doing, the other one should not interfere. So that's why they are critical accesses. So typically you do something like this. You keep a lock, you keep a semaphore, you keep something, and you say that I take the lock, I do these statements, I release the lock. Similarly, the thread 2 can also take a lock, execute these statements, release a lock. Typically, you do something like this. If you had something like this, then what you will ensure is that all the 3 statements of this execute, and then all the 3 statements of this execute. In general, this part that is marked as A does not interleave with this part that is marked as B. So there are no atomicity violations. They run in an atomic fashion. Right? So this is just a general high-level example. What can happen in RTOS kernels? Same problem can happen in RTOS kernels. So let's say you have an application that runs on a helicopter like that IISc helicopter, and these applications which run on these RTOSs, these can directly invoke the APIs of the kernel. They can use it as a part of their application code, right? Kernel also provides them with specific data structures like delay queue, ready queue, things like that. Kernel-owned data structures. And these applications can invoke the APIs that manipulate these data structures. So think of a scenario where this data structure is like that balance variable. It's like a common global shared variables. And an application developer who's working on these RTOS kernels can make a mistake in invoking these read-write operations to these common data structures. So that will end up in a race in the application cost because of the race in the underlying kernel API. So that's what happens. So Avionic, several applications invoke RTOS kernel API to achieve. So applications, let's say, are multitask applications. They have task threads. They can also use interrupt service routines, ISRs, interrupt service routines, in some interleaved fashion. I mean, for now, we worked on a single processor. There is multi-core also, which causes its own weird problems. We won't worry about that now. High-level races in the kernel API will lead to serious undesirable consequences. The other problem is kernels also use specialized synchronization mechanisms. They use callbacks, software interrupts, hardware interrupts, whatever you want. So we modeled HAL RTOS applications with threads as some class of programs. We call them as interrupt-driven programs with callbacks because that's what the kernel APIs are. So we basically assume that any IDC program, an application that uses this kernel, will have certain number of task threads and a certain number of global variables. So there could be task threads of the application, there could be ISR threads, and then there could be callback threads. In addition, there are these several synchronization constructs like disable and interrupt, enable and interrupt, lock preemption, unlock preemption, all kinds of things are there. So I'll just give you an example. I'm not sure how much you can read it, but this is an abstract version of an example. So let's assume that this is a task thread from HAL OS. There's some code it has. And in that process, it also uses a callback thread and an ISR thread. The callback happens to be a time delay callback. ISR is a classical ISR. It just buys time by ticking, counting something. And it is to be noted there that in this piece of code fragment, there are 3 shared variables, which are basically kernel data structures. There's a queue data structure, there's a ready queue, there's a delay queue. All these 3 threads are manipulating those 3 shared variables. That's what they're trying to do. So in this process, so we've modeled the semantics of these programs. I won't go into this. This is like a high-level abstract semantics of the programs. And then there are rules also, so which the kernel API follows. Here are some rules. Task threads can be preempted by other task threads or callback threads. They can be preempted by ISR threads. Callback and ISR threads have the highest priority, so they cannot be preempted, and so on and so forth. Several such rules are there. And what the programmer intends is there is some part here and there is some part here where they do this remove from delay queue, remove from delay queue and stuff like that, insert to ready queue, insert to ready queue. So they want this red color code fragment A and this red color code fragment B as critical accesses to these common kernel data structures. So they should be executed atomically. No interleaving should happen, right? This is irrespective of whether, I mean, the developer has taken care, he's put some lock preemption, unlock preemption here and all. But we would like to do an analysis irrespective of the presence or absence of these kinds of locks, right? So the way we do it is we basically borrow an idea that was presented in a paper by in IISc 19, where they try to come up with what we call a static program analysis based race detection algorithm. So the basic idea is that of a disjoint block. So they say that take the code fragment of different threads in an application, take the control flow graph of the code fragment. I will not be in the position to explain what a control flow graph is, but think of it like a flowchart, extended version of a flowchart. And you say one block of code from one thread is disjoint with another block of code from another thread, provided in every execution of the system, they are guaranteed to execute without interleaving with each other. So this disjoint block analysis is the core idea that we use. And the picture that I'm showing you here is all code fragments that any potential application in HAL-RTOS is likely to use, that we want them to be disjointly executed. So this is done manually by the developer. And now they take a piece of application, they say, I want A and B to be disjointly executed. All that the algorithm checks is whether this block of code A and this block of code B fall into any of these boxes. All these boxes are guaranteed to be disjoint in the sense that if there's a code fragment within this, if there's a code fragment within this, they will never interleave. Right? So suppose the developer is able to mark saying, I want this and this to be disjoint, which the developer should know from a specification. The algorithm basically checks that if this block A and this block B are contained within any of these patterns, right? So that's the algorithm. So you require an IDC program and a set of marked critical accesses. The programmer has to mark it. It's manual effort. Then the code will output a set of potential data races. It does it by performing a disjoint block analysis. And for each conflicting pair, it says if they are in different threads and not covered, then you say they could be potentially racy. So the analysis is sound in the sense that it will output all real races and what suspects to be racy. Then somebody again has to manually analyze whether it's racy or not. So it's only potential race, not exact races. This is unlike dynamic race detection algorithms, which work like testing. If they output a race, there's the real race. Here, static algorithms output only potential races. So here are some notes about algorithm implementation. Marking critical accesses, as I said, is done manually. Then studying, so this developer has to do. Read-write accesses is marked. Locks are used for disjoint block analysis, acquired at the beginning of the block, released at the end. Lock set analysis is available. That was standard C code, so you can do lock set analysis for C code. It's a well-known program analysis technique. And then the algorithm basically checks if each pair of critical accesses are checked. So we started by doing this for HAL-RTOS. The size of the code was about 10,000 lines of RTOS code, and we've also done it for Texas Instruments for free RTOS. And I put these separately and ChibiOS separately because ChibiOS we didn't find a race. In HAL-RTOS, TI-RTOS and free RTOS, we found a race. And free RTOS, the community already knew about it. We posted it. They said, oh yeah, this is, don't worry, it's known to us. TI-RTOS is anyway not maintained now, so nobody responded. HAL-RTOS is critical because it's running. So we found 2 real races, which were subsequently eliminated. So that was the thing. So Sumit, should I finish or? Okay. So I'll briefly talk. So that was one work where we found 2 real data races on a certified operating system of HAL. So that was a cool thing, illustrating the strength of formal methods. So the next thing that we started doing was, again, Abhishek said, oh, like races, I think there are problems with real-time requirements. I'm not very convinced that the RTOS I have. He started out with a developer of the RTOS. Then he became a team lead and then all that stuff. And he said, I am not convinced that my RTOS does timing requirements properly. So let's set out to verify that. And so this again was completely starting from all over the scratch. The RTOS is ERINC 653 compliant. So for an RTOS developer, what it means is that the time that the RTOS takes, processor time, is partitioned. And the processor space, memory, is also partitioned. And things that run within one partition cannot talk to things that run within another partition. They have to develop things very carefully. And that's what ERINC 653 talks about. And so there were HAL operating system has API library. 67 APIs were there to adhere to ERINC 653 specification. And we used UPAL, which is a timed automata based model checker, to verify timing requirements. UPAL is originally developed by Denmark and now hosted by a whole team of universities from Scandinavia. So this is how the picture looks. Application model, HAL OS APIs, then we modeled ERINC 653 requirements as observers, invoked the model checker. And this is, this ... means a lot. This is a very high level view of one of the APIs. So it's called suspend self API. So if you manually model all the 67 APIs in UPAL, this was a challenging task. But we did that, and RTOS requirements were modeled using classical preconditions, post-conditions. This is the course style programming, if you want to know. These were the observers. And basically, we found 34 requirement violations, as it was suspected. Most of them were benign in the sense that it was known and there was no problem. This was as reported by UPAL. But false positives were two. It was wrong because we had abstracted out a bit too much. The important thing was harmful. There were two harmful timing requirement violations, which was found and subsequently eliminated. And so we believe that we made a little more progress towards correct. I mean, at the end of this, you can't say the RTOS is fully correct still. But I believe that this is our first comprehensive effort to verify at least parts of an indigenous operating system. And none of these errors could have found by testing. All of them were because of the strength of formal methods. So yeah, I'll stop here. Thanks for listening.
Thanks, Meenakshi. Now it's time for questions. Please raise your hand who have a question.
Good morning, ma'am. I'm Rishikesh from the Rama Institute of Technology, and I actually have two questions. Firstly, you started by speaking about like AI safety in critical applications. Can AI ever be critically safe as long as they're black box models and we cannot understand what they actually do?
Yeah, see that I didn't talk about AI safety. It was just a one-liner in the beginning of the talk. But what I wanted to say is the formal methods is beginning to be used for AI safety, but it's heavily abstracted. And what people can verify, the models that people can verify are restricted to neural networks with ReLU activation functions, Boolean, manipulations. Nowadays, people do CNNs, abstractions related CNNs, but remember they're all abstractions. Nobody really verifies the actual system. There are some efforts to verify actual camera image inferences, but again, that's heavily relying on abstractions and SAT solvers. So we just, think of it as better than not doing anything, but we're not solving the problem.
And my other question was, so preparing these disjoint blocks, like the number of disjoint blocks would kind of increase exponentially as the software becomes more vast.
No, these are disjoint blocks in the operating system code.
Oh, okay.
The application uses the APIs of the operating system. So this operating system code is fixed. It was 9,600 lines of code approximately. That also takes time. In fact, it took about 130 person-hours to mark the disjoint block by a developer who knows the OS well. So it's not easy.
Would there be some way of automating it, maybe using a data-driven approach types?
Yeah, maybe there is, but yeah, we haven't thought about that.
Thank you.
Anyone else? you have to ask question.
You talk. Hello, ma'am. My name is Jagan. I'm final year BTech student from Christ University. So my question was, you talked about three threats: callback, ISR, and shared variables. You gave the example one about shared variables, but I'm not getting how the callback threat is being affecting.
Yeah, I mean, I didn't explain how what that code was and what it was doing. Basically, I mean, just to give you a high-level intuition of what an operating system works. So, application will have receive some sensor inputs, some inputs and stuff like that, and will process that sensor input. So each such thing, like for example, even in an operating system that runs on a laptop, if I press the enter key, it is processed like an interrupt by an underlying operating system. For the operating system, it's like an interrupt of a certain kind. So it invokes, it suspends whatever it's doing temporarily for that few milliseconds and, tries to process your input by considering it as an interrupt. So in that process, it can consider software interrupts, hardware interrupts, and the scheduler can use callbacks to do some things. So that example had a callback code, but I didn't explain in full detail about what it does. Maybe I could tell you during the tea time what it does.
Anyone else? No question? Okay. If there is one question.
When you say disjoint blocks, so are you going to generate all sorts of permutations and then you look at whether those two disjoint
No,
blocks
so what we mean by disjoint block is an application that the user of this RTOS developer using this RTOS develops will directly invoke some of the kernel APIs that the RTOS provides. So the disjoint blocks are blocks of code that are blocks of code of the application that are within certain kernel API invocation patterns. So inside that, the application code can be anything, but we look for patterns of invocation of the kernel API and mark the disjoint blocks. So it's not dictated by the application.
you have that slide which shows the blocks SM, those are the different patterns.
Yeah, they are fixed. They are fixed for a single core version of the RTOS. Yeah. These are all the kernel API blocks. So if you see the keywords here, it's disable interrupt, enable interrupt, lock preemption, unlock preemption, beginning of a callback thread, ending of a callback thread. These are not dependent on the application.
Yeah, what is this SMT?
That's just name. There's some. S is for schedule and C is for callback.
So these are the different disjoint blocks, right?
For single core version of HAL RTOS. Yeah. Manually marked.
So when you say formal definition, so do you say these are the different interleavings which we test upon and which we check upon and then see whether.
Yeah. They should not be interleaved. They should occur atomically. And if these occur, this is an exhaustive list. If this atomicity violation are ensured for this much, we can ensure that the RTOS is race free.
Any other question? Okay, so if there is no other question, we can thank Meenakshi once again.
Department, we have a small memento for you.
Thank you.
Thank you. Thank you.
That I welcome our next speaker, Yogesh. Yogesh Simhan is an associate professor in the Department of Computational and Data Sciences and a Swarna Jayanti Fellow at the Indian Institute of Science, Bangalore. His research explores scalable software platforms, algorithms, and applications on distributed systems. He has published over 100 peer-reviewed cloud companies, IISc School Challenge Award in 2019 and 2012, and the Distinguished Paper Award at Europa 2018. He is the recipient of IISc Award for Excellence in Scalable Computing Media Researcher in 2020, He is an associate editor-in-chief of the Journal of Parallel and Distributed Systems and an associate editor of Future Generation Computing System (FGCS). Yogesh has a PhD in computer science from Indiana University, Bloomington, and was previously a research assistant professor at the University of Southern California, Los Angeles, and a postdoc at Microsoft Research, San Francisco. He is a distinguished member of ACM, a distinguished contributor of the IEEE Computer Society, and serves on the ACM India Executive Council. With that, over to you.
Thanks a lot. That mic has to be switched. It's off. Okay. All right. Some echo somewhere. Maybe it's me. Let me step away a bit. A very good morning to everyone. And thanks to Sumit for inviting me and to the CSA department for organizing this workshop. So today I'll be talking about some of the research work that goes on in my group, which is the Dream Lab. And I am at the Department of Computational Data Sciences, which is a sister department just across the street. We do have some systems researchers over there as well. And what the work we do in our group is about broadly distributed systems, right? So, which to me, I take a very broad view of what a distributed system is. Anything that has some computing resource and that's spread across the network is a distributed system, right? It could be a cluster, a commodity cluster, like some of the ones that we have in our group. It could be on the cloud, public or private clouds. It could be edge accelerators, which again, we have several of these edge clusters over here, and I'll talk a bit more about these as well. Or it could even be things like drones, which to me are actually flying computers, right? So which are connected through base stations or like point-to-point networking and so on. So all these are various flavors of distributed computing. And one thing that we look to see is how can you sort of make these systems more useful and accessible. So just to give you a flavor of two of these sort of broad classes, right? So one is around the cloud, right? So cloud computing in the last 20 years has completely transformed the way you access large-scale computing. Right? Earlier, you used to have sort of data centers or server rooms that enterprises used to host with a lot of overhead for maintaining your UPS and cooling and so on. We do a little bit of that in our department, so I know how difficult it is, and it's a thankless job. But now with the cloud, enterprises don't have to buy computing and host it in-house, maintain it, manage it, and so on. You can sort of outsource at least the hardware capability, if not more, off to public cloud providers like from Microsoft Azure or AWS and Google and so on, and just lease cloud resources, right, on these data centers. Right? So it's become extremely popular, both for enterprise, even for academia and the scientific domain. But you do have certain challenges, right? So cloud has been very nimble, quickly rolling out new features and so on. But you are starting to see many issues. So one of these is that the diversity of cloud providers means that it's hard to port their applications from one provider to another, right? Even though all these services are exposed to standard HTTP and REST APIs and so on, the moment you start building an application on a single cloud provider, you start using their platforms, you start using their storage systems, and so on. So what conceptually it's possible for you to take your architecture and rebuild it on a different cloud provider. The development cost of doing that is so high that once you start with a particular cloud provider, you effectively are going to be stuck with that, right? So portability is a bit of a challenge, right, across cloud providers. The other one is newer concerns around regulations and data sovereignty, right? And that's all over the world. Overnight, you'll start getting some regulations from some country that says, no, you can't move data out of the country, right? Or you have to have a copy in one location, right? So things like GDPR and its sort of subsequent consequences, even in India, RBI regulations and so on. And with the privacy bill that's being passed and regulations around that that's coming up. It also means that you cannot just pick a cloud provider or pick a data center and start running things. You might have to be deploying your applications or hosting your data across multiple data centers to localize to your particular client base or the data that you're sourcing from. So that's another challenge or concern that's coming up. The other part is also, and this has been around for a while, in terms of if you already have legacy hardware or legacy compute commodity clusters in your own enterprise, or you want to host part of your data within your own data center for privacy reasons or other kinds of constraints. How do you run part of your applications on public clouds as well as private clouds, right? So that you have a seamless experience across them. And as I'll also talk about with the growth of edge and for computing, particularly with 5G being rolled out, operating seamlessly, giving the applications across edge devices as well as the cloud becomes important. So cloud, while it's been transformative in the last 20 years, is starting to confront new kind of shifts that will be good to adapt to. Right? The other perspective is one from the Internet of Things, right? And here again, you're starting to see a lot more sensing capabilities that's all around us, right? So if you go to any building, you'll probably find a dozen, any new building, right? You'll find a dozen different sensors within a single room, monitoring everything that you do, right? Your smart meters at home are nowadays smart meters. Just the other day, they came and replaced our meters in our apartment with a smart meter, right? Which can continuously monitor your power usage and send it to the public utility. You're starting to see traffic cameras all over the place, and Bangalore has about 6,000 of them, which collect real-time data, push it to a private data center that the Bangalore City Police runs, and they have real-time analytics running on top of those. Right? And over time, you're going to start seeing edge hardware, right? Computing hardware co-located with your camera, so that you can do analytics closer to the edge, rather than having to move the data to a private cloud. Right? So this. So one of the key requirements for some of these IoT resources is you need a closed loop cycle, right? You sense, you make decisions based on the sense data, and then you actuate. You actually send a signal maybe to a traffic signal saying that, hey, change the signaling rate because the traffic flow has changed, right? Or they might, in a power grid, they might decide to use a current load to decide whether to purchase power, right? Later on in the day in spot market. You have to handle such loads, right? So which means you're dealing with a scenario where you have potentially millions of sensors. If you take the Bangalore City and smart meters, you probably have 1 million of them easily in residences. And you have sort of edge devices, which can take anywhere from Raspberry Pis to accelerated edge devices, which I'll briefly talk about, as well as the cloud. So how do you work across this continuum, the computing continuum? Right? So from low-class Pi to a high-end, maybe even GPU VM on the cloud. Right? So that brings up a question in terms of, are there ways in which you can make the life of the developer or the end user of such computing resources easier, right? Can you make it easier to program these and deploy these and run and maintain these across such a heterogeneous computing spectrum, right? In a way that is scalable, resilient, and also to some extent privacy preserving. Right? That's something that we work on in our group, where we, in the Dream Lab, we evolve with the hardware. Hardware is not something that we control, at least there are others who work in the architecture space and embedded space who actually have influence on the hardware. We don't claim to do that. But given the hardware and given the heterogeneity of hardware that's coming around, right? And also the evolution of applications, right? So the last 5 to 10 years, ML has been sort of the post chat. Before that, it was something else. Before that, it was something else. And tomorrow it's going to be something else altogether. Right? We don't know, right? So we sitting in the platform, middleware, and algorithm space in between have to evolve both with the hardware and the applications, right? So how can you make it easy to design such emerging applications on top of such emerging distributed hardware? That's really what we focus on. Right? And I'll talk about a few of these in terms of, when you talk about abstractions, you're talking about programming models or approaches to defining your program in a way that is easy to specify, and you get benefits such as portability and scalability and resiliency and parallelizability in an automated manner without you having to learn some complex programming primitives like p-threads and stuff, MPI and so on, right? So which themselves are a form of abstraction. Right? The other is how can you design runtimes that potentially layer on top of existing runtimes to give you some additional features of scalability, resiliency, and so on. Right? So then I'll talk about drill down into two of the projects that we're working on, many others that we have. These sort of encapsulates some of the challenges that I talked about. The first one is going to be on something called Crossfast, which is work that we're doing with IBM Research as part of an open research collaboration. And we have Akash, who recently graduated, and Varad, the current PhD student, as well as the project staff who are working on this project. And the idea over here is to try and understand the first part of the problem we're talking about in terms of distributed clouds, right? Multiple cloud providers, multiple cloud data centers. How can you program the cloud in a more easier manner? Right? And to this end, something that's actually emerged in the last couple of years and it's become very popular in terms of designing applications for the cloud has been this functions as a service, right? And the idea over here is fairly simple, right? So if you want to deploy an application on the cloud, right? You first want to build it as modular building blocks, right? And each of these building blocks could be a single function, right? It could be a single Python function or a JavaScript function or a Java code or so on, right? And that becomes, it has a certain set of input parameters, certain set of output parameters. And what FAS allows you to do is you literally just upload this code, right, with a standard signature provided by the cloud provider. And what they will do, the cloud provider does, they will wrap it around in some kind of a service primitive so that it can be deployed as a REST service, let's say. Right? And this REST service itself will be running within a container, which again, the cloud provider will spin up for you. Right? So it means as an end user, if you want to run a service on the cloud, you don't have to think about the service. You don't have to think about writing sort of REST service bindings, right? You don't have to write Flask code, right, in Python, right? That's taken care of for you. You don't have to worry about spinning up containers. You don't have to worry about spinning up containers to respond to demand, because that's a very key capability on through these fast services. If the request rate for your functions that are deployed increase, the cloud provider is going to automatically scale out the number of containers to respond to that demand, right? And likewise, if there aren't enough requests coming to your service, they're going to shrink the number of containers that are there. Right? And you're charged on a per transaction basis. For each call to your service, you're charged. So which means that if you're developing a mobile app, right, and the mobile app is doing something in the background, let's say you want to crop an image, right, or you want to do some kind of an object detection on an image, right, and most of your mobile apps actually are going to be calling services on the cloud, right? They're not going to be doing it locally, partly because such models might actually bloat the size of your local deployment, right? So most of your mobile apps are not going to work without internet, right? Partly because they're extremely dependent on services on the cloud. So all you do is just take an inferencing model, wrap it as a fast function, put it in the cloud, and use that endpoint in your app. And as requests come in from various deployments of your app, you're going to get just built for that. Okay. So another question? Yeah.
I'm not sure that, but what I got about your idea is you are trying to build a distributed platform,
okay,
in which we can create some small modules of code,
mm-hmm,
and that can be easily distributed within the network to access that very efficiently without having a load in just one center point you are trying to say.
Sort of, right? So part of what you're talking about is already existing, right? So fast functions that
So it is more related to some blockchain technologies also.
No, it's not related to blockchain, right? So we know very little blockchain work on the periphery. See, blockchain is about distributed peer-to-peer systems, right? And that's a whole different thing altogether, right? So blockchain is not as much about, so it's not related to blockchain, let me put it that way, right? This is about just deploying simple functions, right? So you go to any enterprise, or you go to any website, you go to Amazon or Flipkart, right? Behind the scenes, just to load the page, they're going to be running 100 services, right? To give you the current top 10 products, they'll be calling a backend service to give you the current deal of the day. There'll be a service, right? So each widget that you see in your shopping, like your e-commerce page, is likely one or more web service calls that are happening, right? So all these functions have been written, deployed, and managed, right? And that's what we are talking about. How can you do this in a seamless manner, right? You said it has to be, I have to sit and write this entire, for loading a single page, I have to write a single web service. It's going to be extremely heavy, extremely complicated. You'll have 20 owners of that who are all going to be modifying it and getting it to the way. So a way to sort of decompose this is to have much more smaller services, functions as a service, which would be called, let's say, from this front end, in order to present a single page for you. Right? So that's really what we're talking about, right? And that's what comes out of the box today, right? And you also get ways to compose such applications together, so that, because typically, even to run, let's say, just a simple inferencing on an image, You might upload the image, but you might have to do some cropping of the image. Maybe you have to do some scaling of the image. Then the inferencing happens. Maybe you do some post-processing. So even here, it might be a series of these functions that are executed, right? And these might be executed as what's called a workflow within the cloud. A workflow of these functions as a service, right? And these again, in the case of the three big providers, these are typically called AWS has Lambda, Azure has functions, and Google has also functions. And the workflow equivalent of these are typically called step functions, neighborhood functions, and workflows in these three cases, right? So all of this comes out of the box today, right? It's very popular, right? But there are some challenges which we have attempted to sort of address in this particular project, right? One of which is the issue of portability. Right now, if you write a function, so you take your function and you upload it, all the wrappers and so on that are designed are going to be, or even the signatures that you implement are going to be provider specific. Likewise, some of the access to maybe some metadata and so on that your function would get as part of the signatures are also going to be provider specific. So one question, and this is an example, like these are two functions that are defined for, this is a function defined on two different platforms, AWS and Azure, right? And here again, what you get some of these proprietary code that you have to put in if you want to get some specific features. And even the signatures and so on that you get are going to be different. Right? So how can you sort of address this? So that I bring in my function, which is signatures themselves are vendor neutral, right? And some of the proprietary callbacks and so on are again vendor neutral, but I can deploy it in any of these providers. So that's one question. And here again, things like these where I'm doing a call from one function to another function. That again is something that's proprietary. Here in AWS, I have a JSON-based declarative language, which I can define a data flow graph out of. In Azure, I typically have to define a piece of code that actually gives the series of invocations that I do as an orchestrator. Right? So here again, how can I make this workflow definition itself vendor neutral? Right? So that if I want to take the same workflow, run it on AWS or Azure, I don't have to go and rewrite all my workflow functions. Right? So that's one part. How do you ease the developer's cost of writing code? And the other thing is that if tomorrow a new provider comes in, right? I have to go and learn, and if I want to try it out, I have to go and learn all the nuances of that particular provider before I can test it over there. Right? So how can I ease the deployment of my development of my code and deployment of it across these different providers without and be able to go from one to the other if required? That's one part. The second part is from a performance perspective, and this becomes much more tricky, right? At least developers, you can throw people at it and hopefully solve it, right? But what you find, or what we find, is that there's a lot of diversity in the performance that you get for when you deploy these functions on the different providers. And we did some detailed investigation on the two big providers, AWS and Azure. And what you find, and this is for a simple inferencing workload, right? So like workload I told you talked about earlier on. Oops. Okay. This workload is just transforming an image, performing inferencing, and then sending a notification. A simple one. And what you find is that, and these are the same functions that are being executed. The yellow or orange one is AWS, blue one is Azure. So depending on the type of function that you're invoking, the time taken by them is different, right? So what we find in general is that Azure is better at doing heavy compute, because they tend to run directly on VMs. And these are larger VMs, but they are shared among multiple functions. While AWS runs on more sandboxed containers or micro VMs. Right? So because of that, at least that's that we are proposing that because of that, the compute performance of Azure is better, but some of the I/O performance or messaging performance of AWS is better, right? So which means if I have a workflow and I want to run it on a cloud provider, and let's say I have a means to rather either on AWS or Azure. Let's say the programming part is taken care of, right? I have questions which one do I, right? Either I can sit down and do some retail benchmarking, fully functions and workflows and then make a decision. And that starts increasing your required level of expertise, right? Or I can somehow automate it. And that's what we are trying to push for, right? Saying that given any, because the mix of function, and this is just a very simple example, but there are many more such cases in terms of what each function or each platform is for. Right? So can I decide in an intelligent and automated way which cloud provider I want to deploy my functions on my workload? That's one of the other questions. There's one question there, and then we'll come up with
How does different execution model differ from Azure, AWS, and GCP?
So the execution model is not dramatically different, right? All of these have comparable services. You can sort of give a function and package it and deploy it either as a function or composed as a workflow, right? So capability-wise, fundamentally, they're not very different. There are some sort of subtle things. For example, Azure might have a larger message payload that you can exchange. AWS has, no, actually, I should have mistake. AWS has a larger message payload, Azure has a smaller payload, but they allow a larger message automatically through blob-based transfers. So there are subtleties like this, which again, as a developer, you would have to know, right? But they are not really deal breakers, right? So, but fundamentally, I wouldn't say there's anything different, right? Which is what allows you to possibly go across them. Right?
I didn't understand why you have to use either Azure or AWS. Why couldn't you just use Azure where it's better in AWS?
Excellent, right? So, which is what we've done, right? So, good. You're thinking the right way. You're thinking a systems person, a systems optimizer, right? This is what we have done, as you'll see in the next few slides, right? So, you want to do that, right? So, today, if you want to do A, you have to make a lot of support, and B, you have a lot of experience to decide what to do. Right? So, that's when we are on the next slide. That's right over here. Multi-cloud support is missing. And by multi-cloud, we just don't mean that you run on A or B, A even B, for a single workflow, right? So where can I use whichever function is good for one platform, another one's good for a different platform? I don't know. It's not really smart enough that there is going to be a cost for going from one cloud to another. The functions are the same data center, going over what's effectively a private network or local data network. Going across cloud providers, even if it's in the same region, the same geographic region, you're still going across wide area network, which has its own set of limitations and variabilities and costing and so on, right? So that has to be taken into account as well, right? And it's not just for performance or cost that you might want to do this, right? As I mentioned, data sovereignty is a key issue, right? Let's say one part of your database is sitting on one cloud provider, right? But the costing is cheaper on a different cloud provider, right? Can I run part of my function that has data sovereignty restrictions on the one where data is already present, while on the others elsewhere, right? There are different kinds of constraints beyond just performance, time performance, and cost that might require me to run across multiple cloud providers. Right? So given this, as part of this cross-pass project, which by the way is an open source project, I encourage all of you to take a look at it. Can I build a means to give almost zero touch way for you to develop functions as a service and fast workflows, right? That can be automatically and intelligently deployed across a multi-cloud environment, right? And to take us further, this multi-cloud could very well include a private cloud or the edge as well, right? And that's some of our ongoing work. But initially, we focused on the most two big practical cloud providers, AWS and Azure, as part of our work. Right? So some of the contributions are from the code generation perspective, automating it, both for functions as well as workflows, going across both platforms. And how do you decide where to deploy what in order to get optimized performance? Here's a big picture architecture. Systems researchers like these architecture diagrams, so it's mandatory to put one. So you have a workflow that is defined in a generic programming model, right? We have a very simple function interface, which I'll quickly show you. It's just a dictionary for your input and dictionary for your output, as simple as it gets. Right? And you define your workflow itself. It's just a JSON with vertices and edges, and you wire them up. Right? Pretty simple. So let's say you define this, and you submit it, right? And you also give the actual functional logic for each of these functions. So behind the scenes, a few things happen. Right? So one, we actually look at all these functions, and we do sort of either we make use of prior benchmarks that have been run on individual functions, or we do some on-the-fly benchmarking to understand how each of these functions behave on the different platforms. And we decide, based on this, two types of optimizations that we do. One is called function fusion. And what that attempts to do is that if two functions are exchanging a lot of data among them, right? So they have to go through a message queue. There is no way of direct memory transfer of function outputs to the downstream function in fast, right? There's a sandboxing and so on. So it means this has to go to a message queue, and this has to pull from message queue, even if they're running on the same physical machine, right? So that's the different data, right? And if there's a heavy, let's say, a few MB of data that's being transferred between them, that's going to be costly because it's a two-hop data transfer. Right? But since we are the ones who are generating the code, one of the options for us is to actually combine the code for A and B together into a single function. User doesn't see it. When we deploy it, we essentially call A, take the output of A, give it to B, and that becomes a new function, which is the one that's actually deployed in the cloud. So that's called function fusion, and you can do that at different levels of complexity. Right? So that's one fun. The other one is deciding what to place where. Right? And this gets to the other question that was raised. Should I place A in one data center, B in a different data center, C elsewhere, and so on? But that's the second. And not just cloud providers, but data centers of cloud providers are also family. So it's not just a choice of two. It's actually a choice of two cloud providers and many more data centers from all of them. So that's the second part. So these two together are solved as an optimization problem. In order to, again, you can define it in various ways, but what we are currently trying to do is try to meet some kind of a latency threshold while trying to minimize cost. Right? I can also flip it around and say that I want a cost threshold for running the workflow and have a latency as a minimization function. So that's something that we do, and all of this is done on the fly as soon as we get it. And once you decide what you want to deploy, you go ahead and do the deployment. But we also, as part of our deployment, as part of our code generation, we also put in code to generate telemetry, right? Because you want to see real-time performance of these. You've taken a decision and you've deployed it, but is it doing what it's supposed to be doing? Right? Is it performing as well as you expect? Right? So you actually add extra code around the user code before you deploy it to sort of report telemetry in terms of how long the function took to execute, what are the message sizes, and so on. So later on, if you want to go and change your decision, right? Or for future deployment, if you want to improve the deployment intelligence, you can do that. Right? That's essentially power and solution that we get as part of the execution of the system and as part of code generation to help you do. And lastly, you do the generate the actual code and do the deployment as per these decisions that are taken. And here again, we are very careful that we don't reinvent the wheel. Right? In fact, we have not written any custom orchestrator or a DAG orchestrator. That's a complex process, right? And there are hundreds of these out there, and the cloud providers themselves have a built-in orchestrator. That's a fabulous job, right? So you don't want to touch that, right? So what we really want to do is have a light touch operation. Right? So what we do is we split this potentially into multiple sub-DAGs, if you want to call it. And sub-DAGs themselves are deployed within each cloud provider, and they're natively executed by the native orchestrator, ASL and step functions for Amazon and durable functions for Azure, right? So that you get the native performance and native optimizations that are there. We only come in when you go across cloud providers at certain boundary cut points, right, that you have decided. Right? There we automatically generate queues on downstream clouds, and we introduce extra code over here. That's going to take the output of the C and push it to the downstream queue over here. And here I'll have a subscriber that pulls from this queue and triggers the downstream workflow. Right? So these are again additional code and additional services that we deploy in order for you to seamlessly deploy across multiple clouds. Right? So that's effectively what Crosspass. Currently, we have designed it for Python, and these are some examples. This is how you would define your workflow, and this is how you define your function. This is simple dictionary object as input, dictionary object as output, and you can use any input from here, generate this output, and that's all you need to provide as a user. Everything over here is your own code. There's no custom logic other than this. And this is a workflow definition where you're defining your vertices, which are your functions. Let's say it's function 1 and function 2, and you're saying the function 1 is wired to function 2. That's a very simple definition like this. Of course, you can have a more complex DAG as well, a directed basic example for defining a full function. Right? All right, so once you do this, this is we generate the code. Let's say this is the code you're doing. We generate custom code for the different cloud providers, and then we do sort of take decisions on this function fusion. based on various cost models that we have. I'm just going to not going to go into detail of this. I'm more than happy to take questions of that or talk offline. And if we are running across multiple data centers, we generate automated publishers and subscribers along with queues for the deployment. And we also have algorithms for designing this. So that's where the algorithm side of things come in. So in fact, this is from the paper that we published earlier last year. But we have an improved algorithm. This is based on a greedy algorithm. But we have spent a couple of months and came up with a dynamic programming formulation that just gives you an optimal solution as opposed to a greedy solution. Right? So there's enough scope for algorithmic research as well for those who are interested in that. Right? And then you actually do the deployment. So this is an example of one of these workflows for smart grid data analytics that we deployed. As you can see, it's a not-real workflow. All the benchmarking experiments we do is on real clouds, right? It costs a penny, but that's the only way to show that what you've done in systems research. That's one way to do. That we have a talk on some of the theory and earlier on simulations and so on. One of the sort of more convincing ways of showing that your system works is to actually show it work in a real environment, on real clouds, on real hardware, and so on. This is what we did as part of this paper, where we ran this and 3 or 4 other workflows to sort of see how well our system performs, as opposed to a baseline where you might only run on one of these 2 clouds. This is purely to evaluate the splitting performance of this optimization, right? And one of the, just to pull out one example, so one place where our optimizer does better, this is compared to only running on AWS or only running on Azure for this work. If you run only on AWS, there's a performance you'll get. If you run only on Azure, there's a latency performance you'll get, right? But our optimizer is able to pick one combination over here. The circle is slightly off, it should be over here, which is actually about 10 or 15% faster than running it on the others. And this is the end-to-end, including the overhead that you spend for going across the 2 clouds. And we also have interesting results in terms of cost as well. Right? So here we actually, in a greedy formulation, we actually do incrementally, we try to find the Pareto front for this by gradually increasing the cost while seeing how far your time is going to reduce. And what you see is that, again, both Azure and AWS have different trade-offs, right? When it comes to time and cost. Right? It's not like a perfectly uniform system across all of them. So this is the slope for Azure, this is the slope for AWS. So within this, you have to find something that's the sweet spot for your particular application. All right, so to summarize, CrossFast tries to address both the programmability and the deployment of multi-cloud fast workflows. And like I said, it's available in the public domain. It has also got one of the artifact evaluation badges, so at least 2 people in the world have tried it and have been able to reproduce it. So it's not just our lab students. But one of the interesting tangents that we're taking from this, right, is on quantum. So, right? I don't know if quantum has been mentioned in the last 4 days. And I didn't expect to be even talking about this maybe a year back. Last year. So it seemed to it's not right. But one thing that we realized, right, is that quantum computing is just an accelerator. Right? As a systems researcher, I can completely abstract it, right, and see it like I would see a GPU. Right? I don't need to be an expert on GPUs, right? Unless I'm an architecture person, right? To use it, right, or to optimize for it around that, right? And our realization was that most practical application now or in future is not going to be just purely quantum application. Just as no GPU application is purely a GPU application. GPU is just one part of a bigger puzzle, right? Same with quantum, right? So it means you need classical code to use quantum. Classical is a wrapper and quantum is just one piece, or maybe the ones that quantum is optimized for. Right? So it means any application is a quantum plus classical application, a quantum application alone, right? And most of the quantum hardware is going to be hosted on clouds. Right? There are going to be very few installations of quantum hardware outside very tightly managed data centers. These are strategically sensitive hardware, like no one wants to give willy-nilly, right? A bit like supercomputers of today, right? So, or supercomputers of yesteryears, right? Which are very sort of tightly controlled, right? So, which means that being able to design quantum applications on the cloud in an easy manner is an open problem. How many of you have written a quantum code? Maybe one or two, right? I would argue that within 5 minutes, any of you should be able to write a quantum code, right? Without knowing anything about quantum computing, which is what most data scientists do, right? You take a Python library, run it, have no idea what the algorithm does or the model does, right? I'll run it through different ML models. I'll get whichever gets highest accuracy. I'll say, okay, that's the case. You can do the same thing with quantum, right? You can take a dozen different quantum kernels, right? Treat it as a black box, right? Write wrappers around that, right? And run it, and you've written your quantum code. Right? And quantum hardware is accessible, right? For free. I mean, IBM is one of the folks who are making it available, but even AWS and Azure and others are also giving access to quantum hardware. So quantum is there today, real hardware like in real applications. And they're looking to see if CrossFast can be a mechanism to write quantum functions as part of a broader quantum plus classical applications and help developers deploy it. So that's one point. So let's see. So how can you tell me how much time I have? Sir? 5 minutes. 5 minutes. Okay. I'll quickly go through, maybe in a couple of minutes, another topic that I'm working on, and this is to do with distributed programming across edge accelerators for federated learning. Right? So this is work that Rupata, my PhD student, she's leading, along with friends, one of my staff members, and the collaborators at BITS Hyderabad. And the motivation for this is that it's probably sitting in your pockets, right? Anyone who's got an Android phone is currently running a federated learning training, or at least has something deployed for doing federated learning on behalf of Google, right? So if you look at it, right, one of the motivations for federated learning, which actually got a big push from Google a few years back, was the Google keyboard, right? So the Google keyboard does good predictions, auto completions, and corrections, and so on. And it's personalized as well, right? But how do you do these predictions, right? So you might have only typed in a small fraction of all possible words or phrases in the world, but it's able to predict stuff that you have not written before, right? And that's because it's been trained on data sets from every Android device in the world, right? And again, I'm conjecturing, but I'm sure that's mostly true. So all of that used to be pushed to the cloud earlier on, right? Where you do the training, right? Obviously, there's a lot of hoopla around privacy and so on. So the ways that you can address that is by doing the training locally, right? On your local device, on your own phrases and sentences, but send the training model centrally and have these models be aggregated so that you get the same power or almost the same power as having trained a centralized model, but without sharing the data, only by exposing locally trained models. But now that can be expanded to things like smart cities, where I have a video camera sitting on the Satarashanagar police station junction, right? That's capturing all the video. Right now it's being pushed to the cloud, and there the training models and so on. And actually push it, keep the training on the edge using accelerator sensors. Each of these are smaller than the palm of my hand, right? And these have anywhere from a few hundred to even a few thousand CUDA cores over here, right? So yeah, so you have the one over here has 2,000 ampere cores, right? That's comparable to, let's say, to a 3060 that you would have in a workstation, right? And the size of smaller than this, right? Now that can be mounted on a video camera. Right? You can have hundreds or thousands of these out in the field. Can I use that for doing federated learning, right? Not for smartphones, but for more heavier workloads and video and so on. Right? So federated learning, except you got all these devices. Again, these are examples. Visually, they're showing some mobile phones, but this could be any edge resource that's collecting a lot of data, right? You train a local model on your local data. Right? You send that local model to a central network like a cloud, and this model is much less revealing than the original data, right? You can sort of try to deconstruct that model and get some form of synthetic data that has a resemblance to this, so it's not perfect, but at least it doesn't have the raw data. Right? So you get all these local models, and then you do an aggregation on top of the local model and get a global model, G1, which is pushed back to all the local devices, where they again retrain. With the global model as a starting point, you retrain the local data, and you do a few rounds, and this will typically converge to something that's in the ballpark of having trained the global model centrally on all this data. Right? But again, there are many use cases, video analytics, like I mentioned, but also things like medical image data from instruments and utility data from smart meters, banking data, and so on. Lots of applications for doing federated learning. But what we found is that then we spent at least a couple of years trying to use existing federated learning frameworks and found many deficiencies because we wanted to do systems research. We didn't want to worry about the framework too much. We wanted to pick a framework, build on top of that. But we kept finding too many deficiencies. So last summer we sort of took the plunge and said, okay, we're going to build it on our, right? So you don't want to do the decisions lightly, but we were forced to that. And these are some of the reasons, right? So if you look at various capabilities that are available, most existing frameworks are actually not designed for deployment, right? They're designed for ML researchers to run a federated algorithm on a single machine in a pseudo-distributed manner, right? And see if that ML algorithm works, right? They're not designed for systems researchers to actually deploy it on real hardware and get real telemetry on real networks and real compute in order to see if you can improve the performance, right? That is one of the key deficiencies, which we said, okay, we have to build it and run it as a distributed framework so that we can start getting some more interesting research, right? So Federated is this project that's currently going on, and it's highly lightweight. We have run it on Raspberry Pis and can train models comfortably. And you have sort of things like, okay, I won't go into details over here, but just maybe quickly, I'll show you this architecture. Right? So the idea is that you have your local model, your clients running your sort of agent on each of these edge devices, like a Raspberry Pi, or even a Jetson with a few thousand CUDA cores. You have that local data, and you have essentially a means for these edge devices to announce themselves to a central server through an MQTT endpoint as a means of advertisement. They mention what capabilities that they have, what datasets they have, and so on. And then a user deploys an ML model for training. So then they have ways for designing a client selection algorithm. Because these are some of the key pieces that an ML researcher would want to tune, or even a systems researcher might want to tune, right? In terms of which subset of devices do you want to select in a particular training block, right? What kind of aggregation strategy do you want to do, right? And there are dozens of these, and this is where really a lot of systems and ML research gets into in terms of both of these, right? And these are completely modular in our case. You can pick and play with them very easily. And then sort of this, and we also have means for doing model delivery on the fly, so that when you deploy from user perspective, we just have to give the model and the client selection and aggregation algorithm. That's it, right? Model will be shipped over remotely to the available devices that are selected. The different selection algorithms will be used. They will run. You'll monitor them. You'll profile them. You have a lot of telemetry to play around with for optimization later on. You get the result. You aggregate them. You deal with failures by different types of approaches, including checkpointing of your state and so on. And then you sort of finish the round and you get back. But the key point over here is how do you have an interesting framework for doing downstream systems research on top of this by itself, as of now, is not terribly exciting. Right? But the potential for doing more research on top of it is what is exciting. Right? And here's some initial results on these using, so all of these are 6 different algorithms. This, okay, oh yeah, this is IID and non-IID. So we have 4 different algorithms, actually 5, one is missing over here, which we were literally able to do it in a couple of days, right? And these are 4 papers in top-notch venues, and it probably took them a week or 2 or more to code up, and we were able to do it in an afternoon, right? And that's really the power of this, right? So if we want to even validate against an existing platform, it's very easy to take it and re-implement it in this particular platform, right? And again, there's nothing. So we are not making any claims with respect to accuracy or anything. It's just showing that we are able to do it quickly in terms of programmability rather than necessarily the performance. That comes from the original algorithms. All right, so with that, I'll quickly wrap up. So one thing, which has been the intent of this workshop, I'm sure, is that systems research is an exciting area, right? It has been exciting, it will be exciting, and it is exciting, right? Unlike many other domains, right? ML, for example. So I took neural networks as an elective in my undergraduate 25 years back, right? So I took it because I was only elective offered. But point being that and for 20 years, no one reached me. 10, 15 years, no one bothered about that. Right? But I have taken OS courses in my undergraduate and my postgraduate. We teach systems, and that's perennial. Right? It doesn't have a shelf life. It doesn't have expiry date, right? So systems research is exciting, and you work with real systems that you try to understand. These are hard to understand, but it's possible to understand. Unlike it's not an anti-ML stuff. But I see a lot of interesting stuff with respect to distributed systems, clouds, edge, quantum, and so on. So it's an interesting time to begin, right? I think probably the early 2000s, this is the first time systems research is going through big shifts, right? And rapidly, right? So this is exciting, right? Again, a quick acknowledgement to many of my students who have contributed to this, and like very interestingly and in sort of positively for us, many of our PhD students are actually women researchers, right? So this is exciting. So to sort of see that gender balance shift, so they're willing to commit, right, to doing hard work. And we are also supported by various industry candidates. But if you're interested in systems research, what does it take? Right? Because I'm sure some of you are interested in systems research, that's why you're here, and you might be thinking about a career in systems research. Right? So first of all, it requires a lot of persistence and perseverance. It's like Edison said, right? So 99% perspiration and 1% inspiration. That's true for systems research, right? Your idea might be just a couple of weeks of brainstorming, but the work is probably a couple of months of hands-on. Willing to get your hands dirty is important. Stuff is not going to be in a textbook, right? There will be textbook stuff, but there's a lot more beyond textbook stuff that you should be willing to go dig up, talk to people, post on forums, read documentation before you can get things going, right? Being good in data structures, algorithms, extremely important. Good sound fundamentals, OS architecture, extremely important. And yeah, and you should be willing to, you should be excited, right? That's the key point, right? And if you're interested, I'm sure like Vinod and Sumit have mentioned this, various opportunities at IISc in terms of PhD and master's research programs that we have going on. So it's in a month or so, the admissions should open. But we're looking for even internships, long-term internships, not short-term. Systems research takes time, so we can't do much in 3 months, but 6 months, a year, we do stuff. Or research staff position, we have openings in the Dreamland as well. But beyond that, just like there are many such workshops like some of the organized that happen, right, in India, unfortunately. But there are a few of these that happen in an annual basis that you should try and attend. HITC is one of them, just happened in December. And ICDC is another one, just happened last week. But these are two good forums that happen every year, and they have student symposiums and student PhD forums, or even just for students to come participate. There's funding available as well. So try to attend these, right, just to get a flavor of what systems research is, like we got in the last couple of years. And then we are also having something called IIISc that's in the middle of the year to complement these two. It's been a small scale activity so far, but we might be widening up with support from AC Media. That's something to watch out for as well, and maybe during summer. Right? So with that, I'll stop, and if you have some time, happy to take a couple of questions, or we'll go to the coffee break.
Thanks, Yogesh. Let's have a big round of applause. So it's time for ask some questions to Yogesh.
Good morning, sir. Myself, Dr. Arthur Patla, Professor in Computer Science from Desh University, Punjab. Sir, it's a very good thing, sir. We are living in the era of data science and cloud computing. My question is, which one is more secure, more reliable? Among sir, Microsoft Azure, AWS, which one is more secure and reliable, sir? Which kind of, sir?
At least the big three, Microsoft, Azure, and Google, they're more reliable than what you have on campus. Right? And that's really your comparison. Right? Among the three, there's no comparison. All of them are sort of industry standard, follow regulations, all those things. Right? Otherwise, they wouldn't be in business. Right? The moment one of them has one feature, right, the other one is sort of competing for that within the next 1 or 2 weeks or a month. You'll have the same feature there. Right? It's a very cutthroat environment. It's really pity. Right?
Space basically a hard in the market, sir.
Look at the Chinese thing, you can do that. Start meeting business. Not many people are really reaching outside China. And the space is going to be there. It's just not niche player, right? So I think there are, by default, people are going to go to one of these three. And among these three, it might very well boil down to how far you're able to negotiate with a salesperson to get a lower rate, right? To start off, right? Once you get in, you're stuck there, right? IISc is sort of stuck happily so far with Microsoft Azure for the past 5 years. So because it's hard to move from one to the other. It's just a reality. But among these three, there's not really a contest other than pricing and so on. Capability wise, that. Yes.
Hi, sir. My name is Rajesh. I'm from IIITV. Thank you for the excellent presentation. Really enjoyed the experts and the Rotinas. So I have two questions. One regarding XPath. Since it is multiple cloud providers which are going to build on top of a connected architecture, are there any kind of restrictions where you get into, let's say, an Azure cloud to do function ABC, and then for a D you're going into a different cloud?
Yeah.
So how open is that interface itself?
Yeah.
Is the question. Because what you're doing, you're really saying that everything is open. So that is how you're able to connect the pieces and create a meta structure kind of output.
Yeah.
How is that really working?
Right. So by default, all these services are going to use standard HTTP and REST kind of protocols, right? There may be some ways of triggering based on queue-based triggering that might be platform specific. For example, I could on Azure, I could do Azure queue-based triggering of my function rather than HTTP-based triggering. Right? Obviously, that kind of triggering will not work on AWS. You'll have to plug into that SQS or something like that over there. But other than that, or other than, let's say, if you have a hard dependency within your function, you are accessing, let's say, SQL tables on Azure, right? So then you have a hard dependency there, right? You can deploy it on AWS, but you have to literally go across the data center just to execute your function, right? Other than that, the functions themselves are open. The problem is really the code that you have to write is going to be different, right? The protocols are standard protocols, which is why we are able to go from one to the other, right? And we are able to generate the appropriate code to go from one data center to the other. So it's a lot of that part is software engineering, right? It's not necessarily research, but a lot of systems research is advanced software engineering.
Okay, thank you, sir.
Yeah.
The other question I had was you talked about an optimization between runtime and cost.
Yeah.
So is it getting compared with something like NSGA2 or?
I'm not familiar with NSGA2. What's that?
Is it a multi-optimization problem you're solving?
It is a multi-optimization problem. Right? It's a joint optimization problem. But of course, we set one as a constraint and other as the maximization or minimization thing. Right? But we can treat it as a joint optimization also, right? Where you have different ratios that you give to both of these.
Okay, something like epsilon constraint method you're trying out.
I'm not familiar with that, and we haven't tried that. But point being that it is possible to plug in your own optimizer over here. Right? That's okay. The modularity in all these systems, right? The modularity in being able to do more research on top of that is a key value proposition, right? It's not a terminal work. It's a starting point to do more work, and maybe there's a whole research paper to be written just in terms of the optimizations you can do using this framework. Right?
Sure, thank you so much.
Sure.
Any other questions?
Good morning, sir. My name is Joel. I'm a final year undergrad student. My question was related to federated learning. In federated learning, like the models are trained locally and then they are sent on a server, like they're aggregated and like sent out. So, but then always there would be a trade-off because not all the local edge devices would have the resources to train a model.
Yeah.
So, is there something that we can do for optimizing that? Like,
right. So there's a fair bit of ML and systems research at this, right? So if the model that the user gives, that model itself is too large to fit in one of the edge devices that has a local data, right? There have been sort of research that look at sort of dropping certain layers, right, to make the model more simpler, right? Training that simpler model and trying to aggregate that simpler model back into the complex model, right? That's one way. And there are ways in which people have tried to sort of reduce the amount of batch size and so on. Let's say the model itself fits, but you're not able to do sort of all the data sets or the mini batch size is fairly small. You try to reduce the mini batch size. And from a systems research perspective, it's also about client selection. There's a lot of interesting strategies where you might go to this device which is maybe slower or more constrained, only less frequently, but you go to devices that are faster more frequently, right? So that you get a flavor of all the data, but you're not limited by the time spent by the slowest device in a particular round. Right?
Sir, another question was for these federated learning models, like locally trained, are we applying any kind of like privacy preserving algorithms like stochastic?
Right. Now there's a lot of research both on the ML side with respect to some work we're doing with Anirban in terms of how can you do data synthesis. Right? So in a sense, you train a model and actually synthesize data from that model and send the red data. So that way, there's an additional layer of, if you want to think of it as washing, do a double wash or a triple wash before you send the data or the model out of the cloud. Right? There's also work on in terms of things like differential privacy and so on. That also sort of comes into play over here. There's things in terms of homomorphic encryption that's been tried. There's a lot of systems, security, and ML research that's possible to give you. You have to literally think of it as a continuum here as well, right? So it's a trade-off between performance and privacy, right? And you can sort of slide the scale, right? The question is what's your comfort zone with respect to privacy, where you can maximize the performance.
Thank you.
Good morning, sir. I'm Rishikesh from the Rama Institute of Technology. I had a couple of questions. For this user DAG, can we solve it by representing it as a maximum flow problem, the Ford focus and algorithm?
Right. So you in a sense that's one of the possibilities, except that cost is a factor over here. It's not purely about the latency, right? It's about latency. It's almost like you could even solve it using a shortest path algorithm, right? Flow comes into it only if you have, let's say, bandwidth is really a particular bottleneck, but even the bandwidth can be represented as a weight on an edge, and you can solve it using the shortest path problem or the critical path problem, not the shortest path problem, right? But since cost is also involved, right? The critical path, by minimizing the critical path, you might still be increasing the cost beyond a certain threshold, right? So in fact, the greedy algorithm that we solved used a variant of this graph algorithm to sort of come up with all possible paths, looking at the sort of trying to minimize the path cost, right? Using different permutations of placement, right? And then seeing if each of these exceed the cost threshold. If they exceed the cost threshold, you throw away the solution, right? If not, you keep that as a candidate solution, and then look for the best, cheapest among all the solutions. The graph algorithms are one definite technique that you could use for that. Yes.
Got it, sir. My second question would be this choice of different cloud services. Given a particular task or model, can this be automated using some kind of LLMs which can take in all of these as a knowledge base?
Sure. Again, ML is also starting to be a favorite tool for system researchers as well, right? So rather than LLMs, right, which require a large data corpus, possibly Azure and AWS have such large run traces which they could use, right? But not for mere models. Here, something that might be interesting is things like reinforcement learning, right? So where you might want to incrementally do some tracing or select subsets of your tasks and see if that gives you an improvement, better performance. Because right now, the way it's designed, you need to have benchmark data for all the tasks, right? And at least the network links between them. So you run this algorithm, right? But let's say you started off from scratch, right? And you incrementally do benchmarking, get the application running in some suboptimal way so that your result starts flowing in. And then as you start, can you sort of try a few tweaks here and there? And there you could be guided by something like reinforcement learning. Thank you.
Morning, sir. I'm Pratik from PS University, second year. So I had a couple of questions about your ongoing research on programming quantum applications for the platform. So one of the questions was, what kind of applications are you focusing on right now?
Right. So a couple of applications that we are looking at, again, this is driven by collaborators who are more the quantum experts. So one of them is some form of ML training algorithm, an optimization algorithm for ML training, where the core kernel runs on the quantum device, and then you sort of do the gradient descent on the classical part, right? That's one example. The other example is with respect to finding the energy state of hydrogen atoms. That's more from the quantum chemistry side of things. So that's a classic, it's almost like a hello world application for quantum applications. So we're using that as well.
And what kind of potential applications, like quantum applications, do you think would be ideal to explore in the ecosystem?
Right. So again, I don't claim to be an expert on the quantum algorithms side of things, but quantum is typically tends to be good for optimization problems, where the solution space is extremely large and it's able to in parallel try and find that, right? So that's, but there are enough brilliant people in the world who are working on this problem, and we'll sort of go on their coattails. And as there are more interesting applications, fintech seems to be one, logistics and supply chain seems to be another one that people are investing a lot, right? So it's only going to keep growing, and with the hardware also growing, right? In fact, it's arguably going exponentially in terms of how qubits supported. It's like the early days of Moore's law. So which means that quantum hardware is also going to, because right now there are very few, if any, practical quantum applications, right? That can beat classical hardware, right? So quantum is all still, though it's real hardware, it's not real performance, right? So, but hardware is coming, algorithms are coming, people are working with things like noise is a key issue in quantum, because of which you have to run multiple iterations to get distribution of the correct answer. So those are improving as well, so that you can get a faster answer. So all these together, I'm sure is going to shift us in the right direction. Plus policy and strategy as well from the various governments. Right? So that's why, I mean, a year back, if you told me you're going to work in quantum, I'll say it doesn't make sense, right? But today, the light bulb moment went when I wrote my first quantum code that ran on real quantum hardware, right? Because a systems researcher, I want to see or run on real hardware because before I trust it, right? Not just some simulator. Right? And that's possible today, which means that that's something to think about.
My last question is, are there any set of regulations or required specifics for to make a platform ideal for quantum applications to work in, or is it modular enough to flexible enough to adapt for any existing?
Right. So I think we are looking at a few things on the quantum optimization as well. Right? Again, some of these optimizations are understood in the quantum space, but they're not exposed to developers in a meaningful manner. One of which we have as a paper last year on the QC conference is about something called circuit splitting. Right? So typically, quantum applications represented as a circuit, right? And one thing we realized, again, putting on our systems hat, is that there is a lot of queuing time for the quantum hardware. Like again, old HPC hardware as an example. Even today, Sahastra, if you want to run Param Provega, our supercomputer across the street, if you want to run on, let's say, 10,000 cores, you'll probably have a wait time of 2 days. Right? Quantum is like that today, right, for higher qubit machines. Right? So one thing that we realized is the queue time is longer for higher qubit machines and shorter for low qubit machines, because there are way more low qubit machines. Right? So what circuit cutting allows you to do is take a large circuit that requires more qubits and split it into smaller circuits that require less qubits. Right? You get parallelism. That's natural. But more to the parallelism benefit, the queue time benefits are substantially higher. I might wait for 10 minutes for a 7 qubit machine. I might wait for 2 days for a 10 qubit machine. Right? So by running on 2 7 qubit machines, my queue time dramatically reduces. I can get it done quicker. Right? I might have some more noise introduced as a result of the merge and so on. Right? But then I ran it for a few more things, but it's still much faster. So it's stuff like these that, unless you work closely with the quantum folks, as a systems researcher or developer, you may not realize that, right? You may just be saying, oh, I have to wait for 2 days, don't have a choice, right? But this is where the framework, the programming model and runtime framework can automate it for you, right? You come give your code, internally, one of the things optimization we're doing is split it, right? Try different splits and see what's the cost model for it, which is not much different from what we did for multiple clouds, right? Except this is multiple quantum hardware. Right? So we feel some of these optimizations can be pushed easily into something like CrossFast and make it easier for you to write quantum applications.
Thank you, sir.
Sure.
Any other question?
Good morning, sir. My name is Karthik. I am from Jason Academy of Technical Education. Could you please explain the aspect of using rounds for the evaluation of the Pareto front for Azure and I believe it was Google?
AWS and Azure, right? But rounds was in the context of Flotilla, the federated learning. Rounds was not in the context of
Flotilla. It was for cross-platform.
Cross-platform. So Pareto front. So the idea is this, right? So what you Pareto front, for those who are not familiar, it's about if you've got 2 different goals, right? Let's say you want to minimize time and minimize cost, right? So and there's a trade-off between the two, right? What a Pareto front identifies is essentially the set of values, right? For which, if you, let's say there's variable x and y, if you reduce x, right, then y will increase. Or if you reduce y, x will increase, right? So that essentially is the optimality trade-off point, right? Is the Pareto front, right? Which means if you want to maximize constraint one and maximize or minimize the other, it must lie on the Pareto front, right? So what a greedy algorithm tries to do is incrementally start reducing one of the constraints or relaxing one of the constraints and seeing if the other one improves. If it improves, you go ahead. If it doesn't improve, you know it's not in the Pareto front, you go on to the next one, right? That's really how the greedy algorithm works.
Okay, for the rest of the time, we'll stop taking questions now. Of course, they will be around to take your questions. You can discuss more. Let's thank Yogesh once more. We have a small Okay. Thank you. Thank you.
And sorry to put your timetable into a toss.
So with that, we'll go for the tea session. We'll join back exactly in 15 minutes. Okay. Thank you.
Oh, sure.
I got the PPT. I got the PPT.
Got the PPT, right? So, it's
It's a possibility.